Hello everyone. Today we are excited to present our deep learning project for the module SE4050, Deep Learning. Our project is titled Brain Tumor Detection Using Deep Learning Techniques. This project focuses on an important area of healthcare, the early detection of brain tumors using artificial intelligence. Brain tumors are one of the most serious medical conditions that affect people across the world. They can be life-threatening, and in many cases, early detection can make a huge difference in successful treatment and recovery. Traditionally, doctors and radiologists detect brain tumors by manually examining MRI scans. However, this manual process can be very time-consuming, especially when hundreds of images need to be analyzed for a single patient. Moreover, due to human fatigue or variation in experience among radiologists, errors in diagnosis can occur. This highlights the need for automated brain tumor detection systems that can assist medical professionals by identifying abnormalities faster and more accurately. Our main goal in this project is to automatically classify brain MRI images into 4 categories: glioma, meningioma, pituitary tumor, and no tumor, using deep learning models. By doing so, we aim to help doctors make quicker and more reliable decisions based on AI-generated insights. In our research, we implemented and compared 4 supervised learning models. First, we developed a baseline convolutional neural network (CNN) model from scratch. This served as our foundation model to understand how basic CNN architecture performs on this dataset. Next, we used 2 transfer learning models, which are well known for their performance in image classification tasks, VGG19 and InceptionV3. Transfer learning allows us to use pre-trained models that have already learned image features from large datasets like ImageNet. This helps in improving accuracy and reducing training time. Finally, we implemented a YOLOv11n classifier, a model known for its high-speed and real-time image detection capabilities. Although YOLO is commonly used for object detection, we adapted it for classification purposes to see how well it performs in this medical context. By comparing these 4 architectures, our goal was to determine which model performs best in terms of accuracy, precision, recall, and F1 score. Ultimately, this system can support doctors by providing AI-assisted diagnosis, improving accuracy, reducing workload, and saving valuable time in the medical imaging process. For our project, we used the Brain Tumor MRI Dataset from Kaggle, which is a publicly available and widely used dataset for deep learning research. It contains over 7,000 MRI images categorized into 4 classes: glioma, meningioma, pituitary tumor, and no tumor. Each image in the dataset is an MRI slice that represents different views of the brain: axial, coronal, and sagittal. These multiple perspectives allow the models to learn how tumors appear from various angles and positions. One of the strengths of this dataset is that it is balanced, meaning each tumor category has nearly an equal number of samples. This balance prevents the model from being biased toward one specific tumor type and ensures fair training. Moreover, the dataset is composed of high-resolution medical scans captured from real patients, making it suitable for deep learning-based medical image classification. Before training our models, we performed exploratory data analysis to better understand the structure and characteristics of the dataset. We first visualized the class distribution, confirming that each of the 4 categories had roughly the same number of samples. Next, we created sample image grids displaying random MRI scans from each tumor type. This helped us visually differentiate the unique patterns of each tumor. For example, gliomas usually appear as irregular shapes with unclear boundaries, while meningiomas tend to have well-defined edges. Pituitary tumors, on the other hand, are usually found near the center of the brain. By studying these differences, we could better understand what features our models needed to learn. We also plotted image intensity histograms to examine brightness and contrast variations across the dataset. These visualizations helped us design a pre-processing pipeline that normalized image intensities and enhanced feature detection. Once we understood the dataset, we moved on to the pre-processing phase, an essential step for ensuring the model learns effectively. The first step was image resizing. We resized all MRI images to 224 by 224 pixels for models such as CNN, VGG19, and YOLOv11n. InceptionV3, however, required 299 by 299 pixels, as per its input specifications. The second step was normalization. Here, we scaled pixel values between 0 and 1 to help the models converge faster during training. Normalization reduces the computational load and stabilizes the learning process. Next, we performed data augmentation, which involves applying random transformations to increase dataset diversity. We used rotation, zooming, flipping, and brightness adjustments. This helped our models become more robust and prevented overfitting, meaning the models could generalize better to unseen data. Finally, we split the dataset into training, validation, and testing sets, with 70% for training, 10% for validation, and 20% for testing. This division allowed us to properly evaluate how well our models perform on new, unseen MRI images. For training, we used Kara's image data generator to load and augment images in real time. This approach optimized memory usage and ensured each batch of images had sufficient variety. To prevent overfitting, we used regularization techniques such as dropout and L2 regularization. Dropout randomly deactivates neurons during training, forcing the model to learn more general features rather than memorizing the training data. L2 regularization penalizes large weight values, encouraging smoother decision boundaries. Each model was trained using categorical cross-entropy loss and optimized with the Atom Optimizer, which provided efficient gradient updates. We monitored model performance using accuracy, precision, recall, and F1 score as our main evaluation metrics. The main objective of our project was not just to classify MRI scans correctly but also to identify which deep learning model performs best for this task. By comparing CNN, VGG19, InceptionV3, and YOLOv11n, we aimed to balance accuracy, speed, and computational efficiency. Our expectation was that transfer learning models like VGG19 and InceptionV3 would outperform the baseline CNN due to their ability to extract more complex and generalized features. At the same time, YOLOv11n was expected to perform faster due to its lightweight and optimized architecture, which is ideal for real-time analysis. Ultimately, the system we developed can assist radiologists in diagnosing brain tumors more accurately and efficiently. It does not replace doctors but rather serves as a decision support tool, offering a second opinion and helping to identify potential abnormalities in MRI scans quickly. To conclude, our project successfully demonstrates the potential of deep learning in the field of medical imaging. By leveraging CNN, transfer learning models, and YOLO architectures, we explored how AI can contribute to faster and more accurate tumor detection. In future work, we plan to expand our system by incorporating 3D MRI analysis, where multiple slices of a brain scan can be processed together for improved context understanding. We also hope to integrate explainable AI methods, allowing doctors to see exactly which parts of the image influenced the model's decision. This will make AI tools more trustworthy and transparent in medical environments. Through this project, we learned not only about the technical challenges of training deep learning models but also about the real-world impact of applying AI to healthcare problems. Our system provides a step toward intelligent, AI-driven diagnosis, supporting doctors, improving accuracy, and ultimately helping save lives through early tumor detection. Thank you for listening to our presentation.